Hello everyone, welcome to this next video. In this video we are going to see question from December 2018 consisting of 3 marks. The question is, if phi is the solution of this equation, what kind of this equation is? This equation is Volterra integral equation of the first kind, right? Then they are asking what is the value of phi of square root of 2. Among these 4 options, what is the value of phi when evaluated at the point root 2? So let us get started. How can we solve this question? Well, one way is we can convert this first kind of equation into second kind. How we can do that? Because as such there are limited methods to solve for equation of first kind, right? So let us solve this. This is our given integral equation. We can evaluate this equation with respect to x. We can differentiate this. So how can we differentiate any given integral equation? We have to take the derivative on both sides. So that could be taken with the help of Leibniz rule. What does Leibniz rule say? It says if you are to take the derivative of this integration, then what you have to do, you have to perform partial integration, partial differentiation over here of this function, and plus the derivative of x with respect to the derivative of this upper limit with respect to x, and x substituted in place of t, minus the derivative of lower limit, that is 0, that is basically a constant, so this term would ultimately be 0, right? So let us do that. Here in our case the integration is as it is. We'll take the derivative of this term partially with respect to x. That means you are keeping t and this term as constants, right? So what do you obtain from here? So you take the derivative only of this term. The derivative of 1 would be 0, minus x square it would be minus 2x, and then t square it would be 0. The whole thing is multiplied by phi of t. Phi of t is independent of x, remains constant as it is, right? The next term would be the derivative with respect to x of the upper limit, which is x in this case, right? And you have to substitute here in place of t, you have to substitute x. So we just did that, minus 0 accordingly, because the lower limit is 0 constant, and the right hand side gives you x, right? So our equation becomes integration from 0 to x minus 2x phi t dt plus phi x is equal to x, or we can rewrite this equation like this. So we can move this whole term to the right hand side. So this becomes phi of x is equal to x plus 2 integration from 0 to x phi t dt. So here our kernel is x. So one way to solve any integral equation is by the solution by using the successive approximation and by assuming some initial guess. So in this, what we are going to do is that we are taking any initial guess, and usually we take it to be our fx, which is this in our case, which is x, right? Usually we take our initial guess to be fx. So once you have the initial guess, we can successively calculate this phi n x using this expression. That means if you are calculating phi 2, you will plug phi 1 over here. You are calculating phi 3, you will plug whatever phi 2 was from the initial step, and you keep on doing this up to certain n, and then whatever is your phi n x, you take its limit, n goes to infinity, that is your solution. So let us see how this process works. Let us first calculate phi 1. What would be phi 1 according to this formula? It would be x, because fx is x, but and lambda in this case is 2 given in question. You can see our equation, this x plus 2, right? Then integration from 0 to x, this x as it is, and phi naught t. What was phi naught x? our phi naught x was x, so phi naught t is t. So we can simply solve this, integrate this. X could be taken out of this integral sign, then the integration of t would be t square by 2. Limits are from 0 to x. So when you put the limits, you'll have something like this. So this is our phi 1x. Next we'll calculate phi 2x. What is this? This is calculated using the same formula. When we have x plus 2 integration from 0 to x, x phi 1 t dt. Now what is this phi 1? Phi 1 is what we have calculated here, x plus x cube, right? So instead of x we are using the variable t, so it would be t plus t cube, right? So you can take this x common, not common, outside the integration sign, and then you can take the integration. So after performing the integration, you will get something of this sort, right? So in a similar manner, you can calculate phi 3. For calculating phi 3, the formula remains the same. The only difference is that here instead of phi 1, now we have phi 2, right? So we'll put the values of phi 2 t, that would be t plus t cube, taking from here, and it would be t power 5 by 2. We can integrate this and substitute the limit, so we have something of this sort. And then so basically here what you can see, we started with phi naught x, which was x. So next would be phi 1x, that would be x plus something, x plus x cube. The next phi 2x, that was x plus x cube plus x to the power 5 by 2. So we added one more term to it. Next, in phi 3x, you saw in addition to these terms we have an extra term, that is x raised to power 7 by 6. So while calculating the higher terms, you'll ultimately keep on adding various terms to this series. So you have to see some criteria to generalize this so that this thing makes certain sense, right? So can you see some sort of pattern or thing like that from this phi 1x, phi 2x, phi 3x? If not, let us calculate one more term, phi 4x. So with the same process, we end up with this term, right? So here, if you in all the terms x is common, so clearly that could be taken out. I'm trying to generalize this term to reach at phi nx, right? Because we cannot compute all the terms up to n, so that is why. So if I take x to be common, so I'll be left with 1 plus, here would be x square, here would be x power 4 by 2, which could be written like this. Then x power 6 could be written as x square power 3. Then x raised to power 9 could be written 8, because one x is already out, right? So x to the power 8 could be written as x square raised to power 4, and so on. So now do you have some resemblance to any series? So yes, we do have. What is it? You know, e to the power x, what is it? 1 plus x square by 2 factorial plus x cube by 3 factorial, and so on. So we have something of this sort, but instead of x, what do we have? We have x square, right? So you might have guessed until now that what would be our phi nx. Phi nx would be a series of this same sort, x common, 1 plus x square whole square divided by 2 factorial up to x square raised to power n divided by n factorial, right? So this is our phi nx, and what is our final solution? Phi x, that is limit n goes to infinity phi nx. So let me substitute the value of phi nx. So this is the value of phi nx, right? So let me put it here. And if I take the limit n goes to infinity, what would it become? It becomes the infinite series, and we can simply, just as I told you, we can replace that by e to the power x square, right? So this is our final solution phi x, which we were looking for. So in the question they have asked you what is the value of this phi at square root 2. So you just have to replace x with square root 2. So it would be square root 2 e to the power square root 2 square. So it would be this. So let us look at our options. So square root 2 e square is our answer. Square root 2 e square is our answer. So option B is the correct option. That is it for this video. Thank you.